In this video, we're going to look at elastic collisions, which are a special case or a particular category of collisions where momentum is conserved, and so too is kinetic energy. We're going to work to understand when we can talk about elastic collisions so that we can solve all sorts of interesting conservation law problems, not just the ones that we've looked at so far. So the collision spectrum, if you will, not the electromagnetic spectrum, with different colors and frequencies of light, but everything from totally inelastic collisions to perfectly elastic collisions. So the general idea is the more sticky they are, the more inelastic, the more bouncy they are, the more elastic. But the reality is the inelastic side is much bigger. This is objects stick together or don't, maybe kind of do, but mechanical energy is lost. The most extreme versions of this, if you think of a ballistic pendulum, something swings down, it collides and sticks to something, or you fire a projectile into a pendulum and it swings up. If you think about a tackle in football, American football, you are going to collide with someone, hold on to them, and you're going to move together as one afterwards. On the other end of this is perfectly elastic collisions. Mechanical energy is conserved in these collisions, in addition to momentum. Gas molecules colliding, our ideal gas law comes from this idea. Pool balls, in a game of billiards, don't exactly do this, but it's a reasonable approximation. And near miss events, where things we say don't actually collide, very interesting particle physics stuff goes into that category. So what is actually conserved? Well, if things stick together, momentum initial equals momentum final. And that is always true. You'll notice it's on both ends of this spectrum, regardless of type of collision. As long as we're dealing with a momentum conservation system where there's no net external forces on the system that can cause the energy to change, then this will always be true. Kinetic energy is never equal to final kinetic energy unless it's a perfectly elastic collision. And so it's actually better to say, is this a perfectly elastic collision? Well, let's check to see if kinetic energy was conserved. And if it is, then you would know that that is true. So this graphic hopefully helps you out a little bit with this as well. The idea that inelastic collisions are almost all of our collisions, where momentum is conserved, but mechanical energy, kinetic energy is not. But for a very specific set of circumstances, and some that are really interesting and useful to us, elastic collisions where momentum and kinetic energy is conserved. So this is the kind of test you want to get used to doing. Before collision, after collision. Is this an elastic or inelastic collision? So if we've got this information, we've got information before and after. We have initial and final velocities and the masses of the objects. Momentum is conserved, but does kinetic energy equal kinetic initial equal final? We can do the calculation. 1 FmV squared for each of the objects before. Add that up. Total kinetic energy before, 183 joules. And if you do the same after, you get 153 joules. 30 joules of kinetic energy are lost. This is an inelastic collision. They clearly bounced off of each other. They clearly are not going at the same speeds. They're not stuck together, but this is still inelastic because that is the majority of collisions. However, if we were to look at cases where kinetic energy is conserved, we would be able to say some interesting things. If I tell you that these two particles collide elastically, they are a perfectly elastic collision, perfectly elastic collision. We kind of use those terms interchangeably because it's such a narrow band. Then what you could say is, well, initial momentums added together equals the final momentums, right? That's the momentum of the system before and after. And then you have the kinetic energy before and after are the same. And you have two simultaneous equations with all the same variables in them, right? Say you knew the two masses of these objects and you knew their initial velocities, well, then you should have enough information to find their final velocities, right? We can use this, but it turns out that those two equations are a little bit messy, especially with those squared terms in there and masses and everything. What I'm about to show you, notice there's a danger, a warning. It's only good for one-dimensional elastic collisions. You have to be a little bit more careful if you're working in multiple dimensions, and that's okay. You just need to be careful with it. So, conservation of momentum. We're going to rearrange this into a sort of group the initial and final velocities for each mass. Then we do the same kind of thing for our kinetic energy. Here we have an interesting difference of squares. We can divide one by the other, right? Factor things out, cancel out, and you end up with this kind of interesting result, which we can rearrange again to basically say the difference between the velocities before the collision is equal to the difference in the velocities after the collision. And we call this approach and separation velocity. If you imagine, running a race and someone's ahead of you, the rate at which you're either catching up to them or they're pulling away from you at one point is going to be the same as the rate at which you separate from each other once you pass, kind of thing. So elastic collisions are what we call perfectly bouncy, right? All the energy, is conserved. And so we have this nice just swap of velocities. Now, sadly, we're not in class together. I'm going to try to put together a visual demo of this or find a good video of it to show you how you can do this, because you can actually do this in real life with our carts as long as they're colliding with nice springs that behave well, because that's conservative forces, or magnets, which are also a conservative force. You can also do something kind of interesting, and if you put together these to kind of divide one by the other, we get something called the coefficient of restitution. You don't actually need to know this, but basically, if it's between 0 and 1 is where it is. But the closer you are to 1, the bouncier it is, right? If those two things are the same. The closer you are to 0, namely that the final velocity difference is much, much smaller than the initial velocity difference, right? Notice that if they stick together, that would be 0. So that's another way to think about this. A quick example for you, right? If they collide elastically, what are their final velocities? We're going to start with the momentum conservation equation. Then we're going to add in that approach separation velocity equation, which again, you can only use because we know this is perfectly elastic. Notice that's in all caps. If you combine those two equations together, in this case, I'm going to cheat on my, solve symbolically first because I'm solving a system of equations. I'm just going to get some coefficients here. And then this one is a simpler one. I can plug those things in. I can combine them together, do whatever system of equation problem solving you like, and you end up with a final velocity for one, and you can plug in to find the final velocity of the other, right? Do those make sense? Well, does it make sense that the first one would slow down after receiving an impulse backward on it? Yes. Does it make sense that the second one would speed up after being hit from behind? I would say yes, that does. Ball 1 slows down, ball 2 speeds up. That fits. So there are 3 special cases that you want to understand conceptually. What happens if the 2 masses are the same? What happens if mass 1 is much smaller or mass 1 is much bigger? You can do this whole derivation and you can look at it in the slides. But basically, if the masses are the same, they swap velocities. So if one was at rest and the other one was moving and hit it, then the one that does the hitting would stop and the other one would start moving, or their velocities would just exchange. If they're both going at a speed. So a Newton's cradle, which is the classic desk toy where a ball hits down and hits and knocks one up, that's when you can do that. The collision with our cars, which again I will show you when I get a chance to set that up. The other 2 cases are these. We can generally solve to find solutions symbolically. It's a little bit messy and not worth memorizing. But if you think of something really small hitting something really big, then the other thing, right, it'll just bounce off, right? It's as if with perfect elasticity, it just changed direction. That's because the Earth is so massive that you barely notice it. On the other hand, if the ball doing the hitting is huge, then it will cause the small mass to move off at twice the velocity that the first one had originally, which is kind of an interesting thing. So you can also do things where you've got like multiple stacked balls. That's the image, this toy they call the Astro Blaster. Well, each velocity, is twice m1. And so if you keep going and going and going, it accelerates it. So our big 3 cases. If the velocities are the same, again, perfectly elastic collision, or masses are the same, the velocities swap. If mass 1 is really small, mass 2 can be seen as staying at rest, and the other one just kind of flips its direction. If mass 1 is really, really big, and mass 2 is small, then mass 1 just keeps going, and mass 2 goes off at twice the speed that mass 1 was going. All right. On a larger scale, oops, you could do this with a basketball and a tennis ball. This is kind of a fun little one, where if you drop them stacked on each other, this is something you can actually do yourself if you have two balls, a big one and a small one. Right? You get the small ball launched very, very aggressively up into the sky where you can barely see it. But you get the idea. Okay. If you look at an example, two 1 kilogram masses collide elastically, and one stops, then M2 starts. What happens during the collision? How does it actually happen? Right? We know about the before and after. But the reality is, it depends on kind of what forces are interacting. If you imagine there's two springs between them, which is a way of sort of simulating perfectly elastic, because springs are conservative forces. You imagine at some time before they hit, right, the spring is uncompressed. And as you're doing this, right, we have a momentum of 2 Newton seconds and a kinetic energy of 2 joules, right? Spring potential energy is 0. Then when they touch, right, we still have that same scenario just as they come together before the spring is compressed. Then once the spring is compressed, there's some point at which the total momentum is still 2 Newton seconds, but they're both moving together because the spring is fully compressed, right? You can't have anything else, but we have a smaller amount of kinetic energy. And then we have some spring potential energy, right? Some of the energy is in the spring. And then after they push off of each other, right, the momentum is again what it was before, the kinetic energy is what it was before, and the spring potential energy is back to 0. And this continues as it goes. So that's what's actually happening during the collision, before, during, and after. Some of the energy goes into spring potential for a little bit, and then it goes back. So graphically, it looks something like this. The kinetic energy of the system dips and goes back up. The potential energy goes up. So the mechanical energy is conserved throughout, and the kinetic energy is the same at the end. And so I said that the kinetic energy was dropped down to 1 joule. And the question is, how do I know? Well, K is proportional to V squared. So the minimum occurs when the masses have the same speed, because that's when they're going the slowest. And so that's really what we're looking at there. And we can plug in those values. We find out how fast they're going by doing basically a conservation of momentum problem where they stick together briefly, and you end up with 1 joule. Right? So what about an elastic explosion? This is the same idea. Imagine if you compress a spring between two masses, and then they're both at rest and you let them go. Right? This is a problem we could actually have solved at least a little bit, or thought about before, because we know that the spring will apply forces equal and opposite for each of these, right? That's just how forces work. They are always in third law pairs. The spring pushes on one and pushes on the other, equal and opposite. Well, in terms of mechanical energy conservation, we can say, well, we start with 1/2 kx squared, and we end up with the sum of their two kinetic energies. Momentum is also conserved. And so just like we did in our previous discussion about elastic collisions, we can kind of combine those together. We can plug back into one of our equations, and we end up with an interesting result. And this is, again, not anything I would ever consider memorizing, because you don't really need to know this, but know that you could get there. But there is a way to solve this for each of the objects. One of them will be going positive, one of them will be going negative, one of them will be going faster than the other. Notice the one with half the mass is going twice as fast, and so on. So another example of a 1D inelastic collision, right? If these are the unknowns, right? The unknowns don't have to be the velocities. You can actually have other things be unknown. That's perfectly fine, right? There's nothing about the work we've done that requires that. After the collision, we have this information, right? Can we put all that together? Which unknown is the easiest to solve for? Well, if we kind of do the energy equation, that allows us to solve for the velocity pretty quickly. One of them, v2. Then we can do the momentum equation, put everything together, and solve. Right? You can go back and look at this example if you want in more detail. The other thing I wanted to look at is a two-dimensional elastic collision. Now, we know that if you've ever rolled a ball into another ball, marbles, billiards, whatever, you know that things don't always hit and go off in straight lines. If you hit it off center, because they're not actually point particles in space, you can get this kind of result where they fly off in different directions. And so because of that, we need to look at something a little bit more complicated. So in general, the x momentum is conserved and the y momentum is conserved. That must be true. And the total kinetic energy must be conserved. So those are the pieces that we have that have to go together to give us our result. The math is very messy. So we're only going to solve a special case where they have the same mass, right? That way mass cancels out. And if we look at the velocity vector equation, then we get something very simple, right? That. We can then cancel out the 1/2 and the m's in all of these, and we get another simple relationship. What's our conclusion? Well, that V1 has to be moving perpendicular to V2. And that's actually a really interesting result, and something that is useful for us thinking about 2D collisions. You can do this if you've ever taken two coins and sort of hit one. You can do this on your desk. Take two coins that are the same, 2 pennies, 2 quarters, whatever you like. Pennies are easy because they're pretty light, and hit it, and you can watch the path. If you take a little video of it while you're doing it, you can see this happen. So pretty quick, but just a reminder, collisions and explosions are only elastic if mechanical energy is conserved. When in doubt, don't assume.